Welcome to the Better Bricks Interpreting Electric Meter Data Training Series, or it's 10 p.m. Do you know what your power is doing? This training is broken down into 5 parts. This is Session 5, Example of Load Shapes and Common Problems. Some of the typical problems that you can identify by looking at your interval data is finding that you have early morning startup is too soon, your evening shutdown is slow or late, maybe that your weekend schedules are incorrect, or you find out that equipment is starting and stopping when no one's around. You can also find out when controls are reprogrammed wrong. You can detect equipment failures, but also you can prove some energy savings. Let's take a look at some typical problems. In this case here, a customer has installed a new heating, ventilation, and air conditioning system. On November 20th, they called their utility with a high bill complaint. They had a 30% increase in their bill. December 20th, their next bill was 44% higher than that, totaling a 90% increase in their bill. If they had only looked at the interval data, it would have been priceless. So in this case here, if they had had the interval data when they installed their new heating and ventilation system, they would have looked at their previous pattern and all of a sudden noticed that on October 15th, when they installed their new system, there was something seriously wrong. This system was not shutting off most nights. It was running 24 hours a day, 7 days a week. When they finally called with a high bill complaint, their billing period was only covering about half of this increased period. So their next bill was going to be higher. Another thing that happened, when they were working with their building control system people who installed this, they made some additional changes and caused the system to run even higher at almost twice the load for a long period of time. This is when they were supposedly correcting the problem. Unfortunately, this customer didn't have the advantage of having interval data to be able to notice right away that there was an issue or a problem. Even when they seemed to have got their building under control, where now at least it's shutting off at night, their energy usage is still quite a bit higher than it had ever been before with the brand new, more energy efficient system. In this example here, this is an office building that had the control system reprogrammed. And in fact, the program was wrong. If you notice here, the before is the dash line and the after is after the programming. What they had intended to do is to reduce this morning peak, when in fact, by putting the wrong values in the building control system, it caused the building to start up a little bit later, but peak at a lot higher and stay on for a longer period of time until it shuts off, and then even the nighttime load was considerably higher. The good news is this only happened for a couple days before it was noticed and didn't continue for the rest of the billing cycle. This customer was a lot luckier than the last one, although they did have a large increase in their demand usage for that month. This example is a parking garage that had a time clock failure. In this case, this is what a normal weekend looks like. This is the weekday, this is the normal weekend usage. The time clock has the heating and ventilation system of the parking garage shut off because there's no usage during that period of time. So here's the normal weekend load, and here's an example when the time clock failed. The time clock allowed the facility to turn on or off at various times during the weekend instead of staying off all the time. This obviously caused an increase in energy usage. This again was only caught with interval data because just like at 10 p.m. do you know what your power is doing? If you're not there on the weekends, you won't know what's happening either without having something like interval data to review. Now, something more interesting about this example is that a power interruption by a contractor caused this controller to fail in the occupied mode. So because of this failure, the energy usage for this facility stayed on past the normal shutdown times of around 5 o'clock at night. So the energy usage stayed on for the whole evening. Now, although this was caught in a relatively short period of time, when they realized what the problem was, they not only made the contractor come in and fix this controller, but they also could easily calculate the energy usage during this period of time and also charge the contractor for that additional energy usage. You could quickly see that the average usage at night was 400 kW, and for this period of time, for an extra 5 hours at night, it was over 650 kW. So that 250 kW difference for over 10 hours as this continued in the morning, that would be 2,500 kilowatt hours of additional energy usage that the contractor had to pay for. This is another interesting example. When I first talked with this customer told me that their normal operating schedule was 16 hours a day from 4 o'clock in the morning to 8 o'clock at night, just on weekdays. When I looked at this, I was trying to figure out what is going on their weekends. In this case, the weekends are operating 23 hours a day while the building is unoccupied. This happened to be a call center, and what had happened is one weekend they were doing some special cleaning on the weekend and stripping the floors and waxing and replacing some carpets for one weekend. This override was managed by a simple override command in the heating and ventilation system and was left that way for over 14 weeks. This caused a 20% increase in their bill from operating on weekends when nobody was around. Once I brought this to their attention, this customer was able to turn that override off and return to their normal operating schedule. Another comparison you can do with overlaying one year over the previous year is an example like this. In this case, the red is last year, the blue is this year, and this happens to be a school. So we can look and see some good trends. For example, the current year base load, which is in blue, dropped by 30 kW. You can see the difference between shutdown values of last year being about 150 kW to now the current of approximately 120 kW. But offsetting all of that is the current year peak. The current year peak increased by 70 to 120 kW. Now this is in a school district, and the good news about this is this facility added square footage. So they had additional equipment there, serving additional load, which is additional students. They're able to do a good job by decreasing their base load by having some more energy efficient equipment. But their current peak for the new year with the new equipment was higher, so that's expected. That's why it helps to do some documentation of a lot of these changes. Here's another interesting chart or graph, similar to one we saw in the last session, where there's a difference here, in this case, of the shutdown load. Difference between Saturdays and Sundays and other weekend days. So why is the base load so high on some of these shutdown days as compared to others? In this case, it's about a 20 kW difference. What piece of equipment is left running all the time to cause that 20 kW difference? Another question that I would have here is what starts up at 1 o'clock in the morning and runs for just a short period of time and turns off again? On some days, what's been running all night? So the same thing that caused this to run all night could be something that happened here that was left on running during this day. This is an example here of a piece of equipment that ran all night long here. Now this is another load profile. In fact, this happens to be a school. There appears to be something cycling on weekends at night. Every few hours, something's turning on, approximately 20 kW load, and it's turning off again. Granted, this may be normal, but we had one school that found a concession stand heater of about 15 kW that was running all summer long. Somebody had cranked the thermostat up in this concession stand all the way as high as it would go, and even though it was a summer, at night the concession stand would turn on and heat it up to almost 100 degrees inside the concession stand until it turned off again. Accidental changes like this would be easily to recognize that there's an issue or a problem. When using interval data to prove some savings, you can do a comparison like this. These examples came from LPB Energy Consulting that shows a glitch in the optimum start sequence of a digital control system, and it shows the comparison of two different weeks overlaid over top of each other and the savings that were attributed to that. These calculations are fairly easy to do if you have the interval data available. Here's another example of some building shutdown savings. In this example, LPB Energy worked with the custodians to find ways to conserve energy and deliver additional savings. By shutting down the building at the end of the day, significant cost savings were generated for this facility. In this case, at the tune of $23,000 a year. So you can see the difference in the energy usage between the 2 weeks beginning Wednesday, November 17th, and the difference in the energy usage the prior year. Overlaying these 2 different weeks on top of the other weeks helps you find out some of those changes and how they can affect the system and apply some calculations to these to figure out what the energy savings were. There's another example from LPB Energy. In this case here, by finding and solving a simple equipment problem that needed a tune-up, the customers of the school are enjoying a more comfortable classroom environment while the school is saving money. This comparison shows 2 different operating days in the same year with fairly similar weather patterns, but showing you less energy usage for the day that's been after the equipment has had the tune-up. The projected savings of this is between $7,000 and $10,000 a year. So hopefully now you've gone through all 5 parts of the Interpreting Electric Meter Data training series. So remember, the steps to success that we talked about are coming up with a plan, collecting and tracking your utility bills, benchmarking your facilities, setting up interval data metering on the facilities that it makes sense to do, document your operating schedules, figure out what your expected load shape should look like, creating a load profile, and reviewing it along with your utility bills. After you determine items to evaluate further, you take those corrective actions, document some changes made and the results of those changes, and then review it again. Review those changes to the load shapes, make sure the expected changes have happened, and then do it. You've come up with a plan, you need to do the plan, you need to review the plan, and make sure you're successful. Thanks again for finishing part 5 of How to Interpret Electric Meter Data series. Hopefully, you've gone through the other 4 parts. Congratulations, you're on your way to saving energy.